10:30. Let's get started. Are we good with the camera? Yep. Okay. So today we're going to talk about floating point things. I have titled the lecture "How to Survive in a World Where Everything is Wrong," which will hopefully make sense soon. Just some context for today's class. So it used to be that this whole week we talked about these types of things, but as I posted in the README, I have deleted the second lecture that was going to come later this week because the rest of the course was just too rushed and no one was really interested in what I had to say in the second lecture anyways. So I have posted that and you can go read about it. You can read the notes, but I'm just going to turn on the microphone. Feels a bit too loud for me. Okay, can people hear me reasonably? Yeah, okay. So therefore, today's lecture will tie into the course, but weekly, and it'll just be more of a standalone thing that needed to be done in some course somewhere, so we're going to do it today here. Okay, so here's some motivating examples. So for those of you who have not seen this before, it might be surprising, but this thing should be 0. And when you run it, it's not 0. It's just some garbage number. And you might think I'm just messing with you, but you can try this in R or whatever, Java, whatever language you want, you're going to get pretty much the same thing. So here's another one. Two things that look very different because I've added 1, 0, 0, 0, 0, 0, 0. I'm not going to say all the zeros. If I add such a huge number, that should surely change the number. But it's not changing the number. And go ahead, right? Run the code yourself. If you don't believe me, run the code in R if you don't believe me. So this is something that looks horrible, but somehow we haven't really thought much about it until now. So for those of you who've never seen this sort of thing before, may not have noticed until now. So let's figure out what's going on here. So I'll skip this, but you can try it. I'll say, try this. Yeah, so the funny story, in my undergrad, I actually submitted a bug report about this. I was using MATLAB, and I submitted to the MathWorks people who make MATLAB, and I said, hey, your thing is broken. And they were super nice about it, but they were very polite. They were like, just read this. You know, it's normal. So that was just kind of my personal introduction to this, these floating point issues. Okay, so we are going to have to build up to the punchline through the course of the lecture, and we're going to have to start all the way at the beginning of the story, just for those of you who need a refresher, which is binary numbers. So I'm assuming most of you have seen binary numbers before at some point. I'll just do a super quick review. So when we write a number like 562, what we mean by that is 2, 1, 6, 10s, 500s, and so on. And so binary representation is the same thing, except the base is 2 instead of 10. So if I want to write 13, I write it like this, which means you have a 1, 0 2s, 1 4, and 1 8. And indeed, 1 plus 4 plus 8 is 13. Okay, so yes, x is an integer, and we can read this 1, 1, 0, 1 as 1 times 2 to the 3, 1, 8, plus 1, 4, plus 0, 2s, plus 1, 1. And if we had a 5-digit number, we would have a 16, and so on and so forth. So you only need 2 symbols for the binary case, and we just call those symbols 1 and 0 because we already have those symbols, but you could make up other symbols if you want. And we don't need another symbol for 2 because we can already write 2 like this. 1, 0, that would be 2 in binary, so we don't need another symbol. We can write everything we need to write just with those 2 symbols. Okay, any questions about this? Yeah, Jerome.
What about when it gets to like decimals?
Yeah, we will get to decimals soon. So hold on. But first, so numbers are actually stored in your computer, in your memory as binary, right, as bits and bytes, and we've talked a bit about that earlier in the program. So there's actually going to be one bit that's used as the sign bit. It needs to just store if the number is positive or negative. I think it's 1 if it's negative, or it doesn't really matter either way. And so in Python, or in most programming languages, maybe not in Python, we use 64 bits to store an integer. And so we use the words digits, like this is a 3-digit number in base 10, but we need to switch to using the word bits when we're talking about binary. So what you saw up here, this was a 4-bit number. And so if we have 64 bits, it means we can have 64 ones and zeros to represent our number. And just like with the 6-digit number, we have roughly like 1,000,000, 10 to the 6. With the 64-bit number, we can have numbers roughly like 2 to the power of 64. But we need negative numbers, so it's really something like negative 2 to the 63 up to 2 to the 63 are the numbers you could represent with 64 bits. Just like if you had 6 digits, you could have negative 100,000 to negative 99999 to positive 99999. Okay. Yeah, so Python is actually very weird in how it treats integers. So almost every other language, you'll just have a 64-bit integer. If you try to make an integer bigger than this number, it'll just blow up. But Python actually handles this in a sort of fancy dynamic way that it actually allocates more memory if it needs more memory. So it's just being fancy, but that's not really normal, and it's not relevant to what we want to talk about today, and it's just a distraction from what we want to talk about today, but I still wanted you to know about that. Okay, next thing we need to review is scientific notation. So I'm assuming you've all seen this before, but if I have this number, whatever that thing is, I can write it as 2.34 times 10 to the power of 16, and this E16 is going to, that's how we're going to write it in the computer. That E16 means times 10 to the power of 16. So we'll be using this a lot. So now we get to what Jerome wanted, which is, okay, so we can represent integers as binary, but in our computer, if we want to understand something like what's going on with 0.3 minus 0.2 minus 0.1, why was that so weird? We need to understand not just integers, because we're not only just dealing with integers. And so consider this number, this binary number. I'm going to, if you just see a bunch of ones and zeros, you can just assume it's binary, and that's not 101.11, it's the binary version. So consider this number. How are we going to interpret it? Well, if it didn't have the 0.11, it was just 101, then that number would be 5. It would be 1, 4, 0, 2s, 1, 1, 4 plus 1 is 5. However, what does the decimal place do for us in our regular life? Well, if this is the 10 to the 2s, and this is the 10 to the 1s, and this is the 10 to the 0s, this is just the 10 to the negative 1s. That's it. It's just the 1/10. So it's the exact same thing for binary. We have 101.11 is we have a 4, 0 2s, a 1, a half, and a quarter. And so overall, this number is 5.75 in our base 10 way of talking. Any questions about how you get from 101.11 to 5 3/4? Sam?
Yeah, I'm sort of lost on how you got from that number to that number.
Okay, so yeah, I should have said that I turned it sideways. So I turned it sideways just so I could write things better. So I had 101.11, and then I just turned it sideways like this, 101, and I didn't draw the point, but because then I could just write it on the board easier after I turn it sideways. So that's what you see there, 10111. Just so I could say this is the 2 to the 2s, this is the 2 to the 1s, this is the 2 to the 0s, this is the 2 to the negative 1s, and this is the 2 to the negative 2s. So I have 4, 5, 5.5, 5 3/4. I just couldn't, it's harder to write things on the slide without turning it. Yeah?
And just to follow on, so then what do the exponential, like what does 2 to the power of 2 mean in that context?
Well, 2 to the power of 2, it just means 4. So it's just like looking at this number and saying this is the 10 to the 2 position. This 5 actually means 500. And this is the 10 to the 1 position. This 6 actually means 60. This is the 10 to the 0 position. This 2 actually means 2. And this is the 10 to the negative 1 position. This 8 actually means 8/10. So it's all the same except with base 2. So instead of this meaning 100, 10, 1, 1/10, this is the number of 4s, 2s, 1s, halves, and quarters that we have. Other question? Hani?
Is the computer actually storing the decimal?
Is the computer actually storing the decimal? We'll get there. Other questions? Yeah, Alistair.
Does every number have a unique binary representation?
Yeah, every number has a unique binary representation. Okay, let us proceed. So I have an exercise here. Let's not do it right now lest we run out of time later, but essentially, going back to what we were talking about, this is the number of 4s, 2s, 1s, halves, quarters, and eighths, and so you would just need to add those up. So in the 10 case, like we could have 100s, 200s, 300s, 400s, 500s. In the binary case, we only have 2 symbols, 1 or 0, so you can only have a 4 or not have a 4. So it's a little bit different in that sense. But it's still all the same stuff. 1 times 2 to the power of 2 plus 0 times 2 to the power of 1, etc. Okay, we will be using this a lot, so any more questions? Victor.
But it's not with decimals or...
Say it again?
I have a question that is related, but it's not with decimals, it's with letters, because also letters have, as I know, a binary representation. How does a computer know that it's a letter or it's a number?
Yeah, okay. We won't get into that right now, but let's talk about it afterwards.
Okay.
Yeah. I just don't want to run out of time. Okay. Next thing, fixed point. So how can we, let's say we have 64 bits available to us. And by the way, you kind of have to decide in advance how many bits you're going to allocate to the thing you're storing. So most of the things you've seen float, like you've converted a pandas column to type float or whatever. So floating point. But if you have a number that you want to use in your computation, everyone's basically agreed that we're going to use 64 bits to store one of those. It used to be 32, etc. But these days, it's 64 bits. So how are you going to use your 32 bits? So here's one suggestion. Let's use 32 bits on each side of the decimal. So we have like blank, blank, blank. I'm not going to draw 32, but you know, blank, 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 blank. And you could fill in each blank with 1 or 0. And you need to use one of them for positive or negative. So maybe you have 32 over here and 31 over here. And so you could have, 10001.1001 or whatever. So that is called fixed point. It is a real thing, but no one uses it. It's not practical for what we're trying to achieve. And the reason it's not practical is that the biggest number you can store there is around 2 to the 32. And that's not going to cut it. So this is only 4 billion. If you can't have a number bigger than 4 billion in all your machine learning, whatever you're doing, that's going to be a problem because sometimes you need numbers bigger than 4 billion. So you say, oh, okay, that's fine. I'll just use 50 numbers before the decimal place and then only 13 after the decimal place, and that's going to solve it because I have 64 bits. But then the problem is that on the other side, your precision is only 0.0001, and now if you want to store a number smaller than that, you can't, because the smallest thing you could store is 0.00001, and so you're kind of in trouble on either way. Either you can't have big numbers, or you can't have small numbers, and then what we're about to talk about for most of the class is how people have gotten around this trade-off. Tom?
I'm assuming it rounds the last digit on the 32 side? Sorry?
Yes, that's right. There is some rounding happening in that it'll round to the nearest representable number.
Thank you.
Any other questions? So I want you to see that there's this trade-off with fixed point between big numbers and small numbers, and we want to do something about that trade-off. Any ideas about how we can solve this problem? Alistair?
Maybe you could put all the numbers on one side and then just have one thing left over to flip the sign of the exponent. I don't know if that's possible, but like 2 to the 1 and 2 to the negative 1 seem like the same except for the minus sign.
Okay, that is close. That is close. Sam?
Well, I think mine's wrong now that that's close, but
Okay.
I was gonna say you could make it flexible. So if you're saving 1 divided by 3, then you can not make it a fixed point and have it, a point that changes where it is.
There, exactly. Okay, so the idea is instead of saying we're going to have 31 numbers over here and 32 over here, or 50 over here and 13 over here, and just commit to that, let us have the location of the decimal point be floating, hence floating point. So you can put the point in different places, but the problem is we need to spend bits on specifying where the point goes. So this whole journey we're about to go on for the next hour, going into detail, the overall idea is that we're going to save some of our bits for saying where the point goes, and then we're going to put the rest of our bits just doing what we just talked about. Yes, so what you were getting at, Alistair, was a bit less flexible than this, because you were kind of presenting 2 options, but why not just put it anywhere, and we'll say where we want. And then with really big numbers, we'll put the decimal point way over here, and with really small numbers, we'll put the decimal point way over here, so we can get really big numbers when we need them, and really high precision or small numbers when we need them. Questions? Okay, it's going to get messy. Here we go. So everything is going to be represented in scientific notation. So the next observation is that scientific notation, like 5.62, I know not everyone can see. I'm trying to write big and bold. So scientific notation, like we just talked about, is actually what floating point is, what we just talked about. Think about what this means. This, when you write in scientific notation times 10 to the 2, that's saying where to put the decimal point. It's saying this 10 to the 2 means move the decimal point 2 places over this way. And if you had something times 10 to the negative 5, it means move the decimal point 5 places to the left. So all this time we've been writing stuff, blah, times 10 to the something. That's what we've been doing. That 10 to the something is just saying, where do I move the decimal point? If it's positive, I move it to the right. If it's negative, I move it to the left, because that's what multiplying by 10 does. It moves the decimal point, or dividing by 10 moves it the other way. So that's why scientific notation is so fundamental to this discussion, because it is kind of inherently what we're talking about. We're just going to spend some of our bits storing this thing, which is going to be called the Mantissa, and we're going to spend some of our bits storing this thing, which is going to be called the exponent, and that's how it's going to work. However, it just gets a little, one of the most annoying things is that the standard floating point that everyone uses, the people who made it have decided that it's always going to be 1 point something. So that's a particularly unintuitive part about how it works, is instead of allowing us to store any number and then saying where the decimal place is, which may have made more sense, like some giant integer and then move the decimal place to the left or whatever, this is how it works. It's going to be 1 point, and then you're going to have a bunch of bits to represent m. So it could be like 1.0000, or 1.1110011, or 1.0011, whatever. But the 1 point has been pre-decided. And the rest of these bits are called the mantissa, like I said. And then instead of times 10 to the something, it's going to be times 2 to the something, because it's all binary. And this thing is going to be the exponent. And the exponent itself is going to need a sign bit, because the exponent could be positive, meaning it's bigger than 1, or it could be negative, meaning it's smaller than 1. And the bottom part is also going to need a sign bit. So we actually need to spend 2 of our 64 bits just on the signs. The first one saying, is the whole number positive or negative? And the second one is the sign for the exponent, which basically says, is it a big number or a little number? Okay. Pretty much every time I've shown this table, people have not known what I was talking about, but let me try again, nonetheless. I want to show you some numbers and show you how we translate them into this language. So the first number is 2. Every number, we need to transform it into 1 point stuff times 2 to the power of other stuff. That's what we need to do every time. And so number 2 is going to be 1.0 times 2 to the power of 1, because 1 times 2 is 2. And so in binary, that actually looks the same, because it's just 0 and 1. So the mantissa is 0. That's this right here. And the exponent is 1. That's this right here. OK, that seems... well, yeah, let me take questions first. I hear some whispering. Okay. Let's go through the second one. So second one, the number 10. So I'm talking about our base 10, number 10, like this many things, not 1, 0. Here's how we have to write it in scientific notation. This is where it gets not intuitive. The way we have to write this is, it's, again, 1 point something. So it's going to be 1 1/4 times 8. Because that's the way you get 10 out of this system. It seems very unnatural to us, but and in fact, going back to your question, Alistair, this is the unique way of representing it in this format. Is 1, because the 1 point something always has to be between 1 and 2. That's why it's unique, because it could be 1.0, that's the least it could be, or 1.111111111, which is almost 2. And so it's always got to be between 1 and 2. And then you just shift the decimal place over. So it has to be 1 1/4 times 8, because it can't be something times 4 or something times 16. Yeah, Derek.
Let's say scientific notation base 2.
Well, no. So just the fact that I'm using symbols like 5 and 3 means I'm just saying the set of symbols I'm using are the 0 through 9 symbols. That's what I mean by base 10 up here, like base 10 symbols. And then if I need to write that in binary symbols, now 1 1/4 looks like this, 1.01, because that's 1 and 0 halves and 1/4 times 2 to the, and then the way we write 3 is 1, 1, because that's 2 plus 1. So now what is the mantissa? I'm just reading off this thing, 0, 1. And what is the exponent? I'm just reading off this thing, 1, 1. More questions? Yeah, Annie.
You said that the base 10 just means the exponent number has to be between 1 and 9 or 0 and 9?
Yeah, with base 10, I'm using the symbols from 0 to 9, all the symbols. Reiko?
Is there a systematic way to get from 1.25 times 2 to the power 3 to 1.01 times 2 to the power 3?
Yes, there is a systematic way to convert between base 10 and base 2. I just don't think we're going to have time to go through it, but we can post a link or something. Okay, so I have a couple more examples here. 0.375 again. 0.375 is 1.5 divided by 4. It's 1.5 times 1/4. So yeah, it's a little mind-bending, but the way we would then write that in binary is 1.5 times 2 to the, and then the way we want to write 2 is 1, 0, and okay, that one's not very important. The last one is very important. Let's talk about the last one. The last one is where all these errors are coming from that you saw at the beginning of class. So 0.1 seems like a perfectly innocent, friendly number in our day-to-day life. 0.1, nothing weird about it, right? But when you try to write it like this, you say it's 1.6 times 2 to the negative 4. That is to say 1.6 times 1/16th, which is to say, so you basically divide that by 4 times. You get 0.8, 0.4, 0.2, 0.1. So it's 1.6 times 2 to the power of negative 4. But how do you write 1.6 in this thing? Well, it's 1, and then you have a half, because 0.6 is more than a half. And then you don't have any quarters. That'd be too big. 1.75 is too big. You don't have any eighths. But then you have a 16th, and you have a 32nd, and you'll just go crazy thinking about this. But in fact, 1.6, when converted to binary, is an infinitely repeating thing. And maybe that's even the pattern. 1.100110011. I don't know if it just goes like that forever, 0011. And you might be very offended by this because you might say, well, 1.6 is such a reasonable number. Why do I need an infinitely repeating thing to represent this in binary? Binary is junk. I don't want to use binary anymore. But that's not a correct way of thinking. We're just biased on our base 10 way of doing things. And actually, all these systems are kind of equally bad in a sense. For example, in our system, 1/3 also seems like a perfectly nice number. But in our base 10, we can't represent 1/3. It's 0.3333 forever. And that's the exact same thing that's happening here. So different systems are going to have different numbers that turn into infinitely repeating decimals. But imagine you're using a fixed point or a floating point or whatever system in base 10, and you have to represent 1/3. There's going to be a rounding error there too, because you're going to run out of bits. You're going to go 0.33333, as many bits as you have, 64 bits, and that's going to be wrong, because you need infinitely more 3s for it to be correct. And so when you start doing computation with those numbers, then things are going to be wrong, and those errors might compound in weird ways, and you might get surprising results like we got at the beginning. And that's exactly what's happening here, except the numbers that cause this to happen aren't the ones we're used to, because things like 0.1 and 1.6 sound normal to us, but actually in binary they are infinitely repeating. Questions or comments? Tani?
This might be a bit more than we need to touch on, but how does binary do better with things like pi and other elements?
Does binary do better with things like pi and stuff? I don't think so, not particularly. I think what really matters is just how many bits you have. And yeah, I mean, so yeah, but let's not get into it further. Other thoughts? Yes.
So in these set,
Vignesh, right?
yeah.
Okay.
So these are basically rational numbers. So if we do have some which repeat and some which don't, are there any benefits between the two in terms of representation?
Well, that's the thing. You can't just say these are numbers that repeat and these are numbers that don't, because it depends on what base you're talking about. So actually, all we care about from now on is binary. And so there's numbers that repeat in binary and numbers that don't. And yes, the numbers that repeat in binary are going to be rounded off when they're stored, and the numbers that don't aren't. And so that's better. But like, you're not going to adapt your machine learning model to take that into account. You're just going to try to do whatever you want to do and hope that it kind of works out. So, and usually it does, but that's what we still need to talk about cases where it doesn't. Rob?
Yeah. So just how does like 1 point, like in the second one, a binary scientific notation?
Here.
How does that end up being 10?
Right here?
Yeah.
It ends up being 10 because 10 is 1 1/4 times 8. And to represent our 1 1/4, we need 1.01, because that's a 1 and 0 halves and a quarter, and then times 2 to the 3 to get 8. And that's how we write 3 with 1, 1. Are you convinced?
I'll think about it.
You'll think about it. Okay, last question. Carrie.
Are repeating decimals in our conventional way of writing things also going to be repeating in binary? So
Are repeating decimals in base 10 going to also be repeating decimals in binary?
so like, could you do 1/3 in binary?
Yeah. Not necessarily, but I'm not too sure about that. Yeah. Okay, let's keep going. All right, so this thing, the IEEE floating point standard, is the thing everyone uses. All the programming languages, whatever, they all use the same thing. So some people decided that they're going to use 53 bits for the mantissa and 11 bits for the exponent. So now you know. You basically now know everything, and in your lab there's an optional question where you actually need to go and compute what is the biggest possible number, what is the smallest possible number, just based on this information, and then you can kind of try it and see if it was true. But you basically know everything there is to know, because it's really just a matter of these two numbers, 53 and 11. That's how they decided it. If they had picked, way more bits for the mantissa and only like 2 bits for the exponent, you wouldn't have to be able to get very big numbers because you couldn't move the decimal place that much. If you put everything in the exponent, you couldn't get high precision, and so there's this trade-off. They decided that you have 11 bits. And don't think that means you can only move the decimal place 11 places. It means you can move the decimal place 2 to the 11 places. Because you have an 11-bit binary number storing the exponent, so you can have numbers sort of like 2 to the 11, which is like 1,000-ish. So it means you can move the decimal place 1,000-ish places in either direction. I know that's starting to sound pretty good, because you can get pretty big numbers by moving the decimal place 1,000 positions. Was there a question, Reka?
Yeah, I just wanted to ask. So basically, you're setting a set number of bits aside for the mantissa, and then some for the exponent, but it's floating in a sense because you have 11 bits for the exponent.
Exactly. So the 53 and 11, that's set in stone, but it is floating in the sense that you can set those 11 bits to whatever you want, and our interpretation as humans is that we have floated the decimal point when we think about those numbers. Yes?
If we have 64 bits number, so we just want to move 64 decimal points, right? So,
okay. Yeah, sorry. There's 2 different things. There's the number of bits in the computer that we are going to, that we have to store. Like we have 64 ones and zeros. And then there's the actual numbers themselves, like in our minds. In this case, those 2 are the same because, but in floating point it's different because you think about this. Think about base 10. It's easier to think about in base 10. So if you had times 10 to the 20, I only used 5 numbers to write this, 5, 6, 2, and 20. But this number is 5, 6, 2, 0, 0, 0, 0, 0, 0, 0, 0. So it's a 20-digit number. That's different than, but I only used 5 numbers stored in the computer. So that's what was happening with you. 64 is the number of numbers being stored in the computer, but I can move now the decimal way more than 64 places and have numbers way bigger than that.
But if we want to move only to, what is the maximum exponent that you want to replace?
Well, that's the thing. What is the maximum exponent? The people who designed this had to decide. So they decided, as you'll see in a minute, that the biggest number is going to be around 10 to the 300. So 10.0, just putting the 0.0. So that's okay, and this is going to break. So they had to decide what was reasonable, and someone decided 10 to the 300 is a pretty big number, and that comes from this 11 in the mantissa, because one of those is the sign bit, the other, in the exponent. One is the sign bit, you have around 10 left, so that can be around 1,000. 2 to the 1,000 is around 10 to the 300, and then you get that behavior. But let's move on. Okay, this code is just some code that I pieced together where you can call this binary function, and it'll print out the bits that are stored under the hood, and you can actually see what's happening. So you could play around with this if you're interested, like the number 2. is 1.0 times 2 to the 1. The way it actually stores the exponent is it stores the exponent as an integer, but it stores the plus 1023. But if you want to see how 10 is stored, like I talked about before, is 1 1/4 times 8. So you can really go into the bits under the hood, and you can see, oh, there's the quarter right here, and so on and so forth. So I'm not going to dwell on this right now. But if you're interested in really digging, there's that repeating decimal, by the way. So it really is 1100. So if you're interested in digging into this more, play around with this function that I provided for you. It's showing you the actual bits, and you can relate them to what we've discussed. So that's all pretty nice. Okay, some take-home messages. Numbers are not represented exactly. There's round-off happening all the time because of infinitely repeating things or just too much precision and you can't fit it anymore. You do not get an error message or a warning when this happens, because otherwise every line of code would have an error message or a warning, because as soon as you did 0.1 enter, that's already getting rounded before you even do anything with it, as we just saw. So you have to be pretty careful. Most numbers, in fact, very few numbers can be perfectly exactly represented. Most things you type in are getting rounded immediately without telling you. Even most integers cannot be perfectly represented as floating point numbers, as we will see soon. There is a biggest number. There is a smallest number. And these biggest numbers and smallest numbers are quite consistent because pretty much everyone is using this IEEE double precision floating point system. Okay, let's resume at 11:11. So when you're reading these printouts here, the exponent is not actually stored as a signed integer. There's no sign bit for the exponent. The possible exponents are from negative 1023 to positive 1024. Instead of storing that with the sign bit, they've just stored it as an integer. So this is really just an 11-bit integer in binary, which means it goes from 0 to 2047. And then you have to subtract half of that range. You have to subtract 1023 from that integer. This is optional. You can tune me out if you're not interested. But like, for example, here, this number is 1024 plus 2, so that's 1026. Then you have to subtract 1023 to get the actual exponent, which is 3. And same thing here. This crazy looking number is 1019. You subtract 1023 and you get the actual exponent of negative 4. So if you're really interested in interpreting these printouts I made for you, that is the situation there. Questions? Okay, onward. Spacing between numbers. So, let me go up. Okay, let's go back to base 10. I always like to go back to base 10. I do not like those numbers getting confused with the actual numbers. Let's go back to base 10, and I'm going to ask you the following question. Let's say you were doing a situation like this where you only had 3 spots after the decimal point. Okay, so you had, I guess, 3 digits in your Mantissa. So here's 8.982. What is the next largest number I could store that's bigger than 8.982?
8.983.
8.983, yes. The smallest change I can make to that is just taking the least significant number there at the very end and upping it by 1. So 8.982, the next biggest number is 8.983. That's the smallest change I can make. So what is the difference between those? It's 0.001. It's 1/1000. Okay, how about this one? 3.432 times 10 to the 2. Let's assume that the 10 to the 2 is frozen there. We can't change the 10 to the 2. What is the next biggest number there?
3 instead of 2.
3.433. Again, I'll just take the least significant digit and increment it by 1. But there, the difference between the current number and the next largest number is actually 0.1, because it's it's what are those numbers actually? They're 343.2 and 343.3. And so the next largest number, bigger than 304, is actually 0.1 bigger. So the gap between the number we're representing and the next biggest number is a larger gap here. Last one, we have 0.001 times 10 to the 1. The next biggest number is 0.002 times 10 to the 1. What are those numbers? Actually, they're 0.01 and 0.02, and so the difference between them is 0.01. So in short, when you have bigger numbers, there's going to be a bigger exponent. Because if I have 1 billion, I'm going to have a big exponent sitting there because I have had to move the decimal point to the right. And when I have bigger numbers and therefore bigger exponents, I have a bigger spacing between numbers. Because remember, not all numbers are representable. Like you cannot have 8.9825 here. That's just not allowed. We don't have enough spots to do that. And so it's the same thing in your computer in floating point. It turns out the spacing between the current number and the next number is an extremely important, probably the most important thing to know when you're doing calculations. Because the round off, the errors are usually going to happen when your real answer lies somewhere in the middle and it rounds to one side or the other. And if you have a huge gap between the number you're dealing with and the next number, there's so much space in the middle that your real answer could lie in and then get rounded really far to the nearest number, and that's where you get those big errors. And that's, in fact, what's happening. Let me just scroll all the way for a minute and then I'll come back. That's what's happening here. This number has a massive exponent because it's such a big number. And so just like what I just showed you, you make the smallest little change to it. You change that last digit from a 0 to a 1 or whatever. That little change is getting multiplied by a massive exponent. And so, first of all, that 10 to the 40 itself may not be represented exactly in binary. But it itself may be rounded. Nonetheless, the number after it is pretty far away. And so it's so far away, the number after it, that when I add that ridiculous thing to it, it's like here I am, 10 to the 40. Here's 10 to the 40. Here's the next number after 10 to the 40. And I add that ridiculously huge thing, I only get this far across the chasm. And then I round back to 10 to the 40. And that's exactly why this returns true here. And that's exactly why you care about what the spacing is between the current number and the next number, because your calculations fall in that chasm and they round the best possible way, but you can still get these kind of crazy looking results. So let's proceed here. Furthermore, I should say not only we can be much more precise. We don't just have to say bigger numbers have bigger spacing. We can make a much more precise statement, which is that the spacing is precisely the smallest possible change in the mantissa, in that case 0.001 times the exponent. That is precisely the spacing between the current number and the next number. So in my base 10 example, it's going to be 0.001 times 10 to the whatever that exponent is. That's the spacing. End of story. So it's not just, it vaguely gets bigger, but it exactly gets bigger. And here's what that function looks like. It looks like this. So how do we interpret this? Well, basically, you're going along here. You're making your number bigger and bigger and bigger. You're just changing the mantissa. The mantissa is getting bigger and bigger and bigger. But eventually, you hit the end of 1.1111111, and you need to move on to the next exponent. So you increment the exponent by 1 and go back to 1.0000. And that's this jump here. So again, this is plotting that gap, that spacing versus the number itself. And basically, every time your exponent ticks up by 1, because you've reached the end of your mantissa, that spacing jumps. Now, this is actually a little more detailed than we really care about, because in general, in life, we don't care about the exact spacing between the current number, we just care about a trend. And the trend is roughly that the spacing is proportional to the number itself. That's just like the y equals x line. Because if I make my number, twice as big, then the exponent is going to be bigger by 1 more, and the spacing will be twice as big. So this really staircase thing is a detail that we can ignore, and the take home from it is that the spacing is proportional to the number itself. So if my number is 1,000,000 times bigger, the spacing will be 1,000,000 times bigger. Maybe not exactly because of the staircase effect, but we don't really care. Questions? Okay, that's probably a bad sign, but that's okay. So, going back up here, we said that the space, like for example, this number that didn't have any exponent, it just had times 10 to the 0. We don't bother writing times 10 to the 0. The spacing was just 0.001 for that number at the top, 8.982. And so it was, because we had 3 things in our mantissa, and so it's 10 to the negative 3. We just talked about earlier that we have, whatever it was, 51, what was it? 53 bits in our mantissa in the real floating point number, but one of those is a sign bit, so we really has 52 spots after the decimal in our real system. And so the spacing at the number 1 is around 2 to the negative 52. So that means the next biggest number that you can represent, bigger than 1, is 1.222, etc., etc. I'm sorry. Times 10 to the negative 16, so a bunch of zeros. So let me rephrase that. The next biggest number after 1 is 1 plus that. 2 times 10 to the negative 16. So if you want, 1 plus 2 times 10 to the negative 20, you're not going to be able to... 10 times 10 to the negative 16. I'm sorry, I'm getting myself confused. 2 to the negative 52 is roughly 10 to the negative 16. But in our human terms, we more care about talking about 10 to the power of something, because that's what we deal with in everyday life. So the next biggest number after 1 will be around 1 plus 10 to the negative 16. So if you want 1 plus 10 to the negative 20, you're not going to be able to get it, because the spacing is too big. And we can just do that experiment like we did before. 10 to the negative 20, and we're going to get the same thing. Again, the spacing between 1 and the next number is around 10 to the negative 16, because that comes from 2 to the negative 52, because we had 52 bits in the mantissa. So we've kind of derived from knowing how it works the behavior of the computational environment, which is pretty satisfying, I find at least, because I could kind of predict when things are going to go wrong now by just knowing this. All you really need to do is remember 10 to the negative 16 and you're basically done. Because now, what is the error around 1? It's around 10 to the negative 16. If your number is 1,000,000, which is 10 to the 6, your error is going to be around 10 to the negative 10. Because it's 1,000,000, 10 to the 6, times 10 to the negative 16 is 10 to the negative 10.
Can you explain again what you mean by this is the spacing of 1?
Yes. Okay, so point 1 is that you can't represent every number. You can only represent certain numbers. And then, so you have a number that you can represent, and then this dead space of numbers you can't represent, and then another number that you can represent, and then another number that you can represent. What I was showing you earlier is as the numbers themselves get bigger, that spacing gets bigger. So it's kind of like number, 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 number. And so what you want to know where, at the number you're dealing with, what that spacing is, because the errors are going to be of that magnitude. And so when I say this is the spacing at 1, I mean if you have the number 1, then the next number will be roughly, that gap will be roughly 10 to the negative 16 between 1 and the next number. Which is why, also, going back to that 0.3 thing from the beginning, these numbers are around 1/10, so I'm expecting errors to be around 10 to the negative 17. And hopefully, that's what we get. Yes, so the errors are around 10 to the negative 17, because the spacing between numbers around a tenth is around 10 to the negative 17, and the error is basically similar to the spacing. Because all this error is coming from you're kind of rounding yourselves off, or landing and rounding and all those kinds of things. So going back to the very top again, when I did this error was around 10 to the negative 17. I multiplied by 10 to the 20 to get something around a few thousand, just so it would look more dramatic. Last year I did this. but I think it looked more dramatic this way because you get some thousands, which looks really troubling for something that should be 0. Sorry about the scrolling. Okay, yeah, more questions? Yes.
Does it round only to the lowest number?
No, it rounds to the nearest number.
But if you see the graph, it is like below the x, y equal to
Yeah, that's not that. That's something else. That's the fact that when you're here, you keep the same spacing until you get up to the next. It's an unrelated thing. Yeah. Other questions? Okay, so here's the thing. If I'm losing you or losing your interest here, this is the take-home message at the bottom. When you're doing stuff, you can expect errors that are approximately the stuff you're doing times 10 to the negative 16. That's like the one take-home message from this lecture if there's going to be one. So you can expect that kind of thing to happen and should be aware. Okay, so here's some fun examples in terms of the order of operations, which really throws people off. So I have a lot of fun with these. Look at this. 10 to the 16 plus 1 equals 1 plus 10 to the 16 plus 10 to the 16. You've been told since grade 3 or whatever that the order doesn't matter when you're adding things up. But hey, false. So how does this relate to everything we've just been talking about? I never said anything about order, but actually, here's why. I have picked 10 to the 16 purposely to make this thing happen. And here's why. So here's the first part. 1 plus 1 plus 10 to the 16 is not equaling 10 to the 16. That's like good, right? We're happy with that. And then the next part is this part. And that's the part we're not happy with. So the reason why these are false is that the one on the left appears to be just equal to 10 to the 16 itself, whereas the one on the right seems to be different. I'm not saying it's perfect, but at least it's different, which is good, because we would really love this to be false. So let me explain. I have picked this number in a kind of evil way, 10 to the 16, knowing that, remember I said 10 to the negative 16 is the magic number. So 10 to the 16 times 10 to the negative 16 is 1. So around 10 to the 16, the gap between that and the next number is around 1. And I've picked it just right, so when I'm at 10 to the 16 and I add 1 to it, it just doesn't make it halfway to the next number, so it rounds back down to 10 to the 16. And that's why we have that true here. I can actually add 1 to it as many times as I want, and because the order is happening left to right, I just add a 1, but it rounds back down. I add 1 again, it rounds back down again, and I can do that all day long and nothing is happening. But thanks to this precise choice, 2 is enough to get across that gap. When I add 10 to the 16 plus 2, it goes more than halfway to the next number, and it rounds up to the next number, which is close to 10 to the 16 plus 2. And so that's why you get this funny thing at the top, that the order matters. Questions or comments? Jerome.
So if you put the first line that's false, if you had the ones in brackets.
Yes, absolutely. If you had the ones in parentheses, you will get true. So that's all it is. It's not about the left or the right, it's about the ones combining together to form a great enough number to make it over the gap. Yeah, so when you're literally just adding two numbers, a plus b or b plus a, it makes no difference. There's no situation in which a plus b or b plus a are different, unless someone like overwrote the definition of plus or something. But it's something else here that's happening. Anyone else?
Are we going to learn like when to realize that this is affecting us when we're doing?
Are we going to learn when to realize this is affecting us? A little bit, yeah. in the remaining time today. So let's keep going. Okay, so these notes are things I already talked about verbally, so we can skip over those. Oh, hey, Jerome, there you go. It was already in there. Yeah, so that works out nicely. What is this anyways? Yes, this is just adding 1 over and over again 100,000 times just for fun. And it still stays at 10 to the 16, sure. And then this was the thing at the beginning. And now I know how many zeros I can add here. I can add about 24 zeros to this ridiculous number and preserve this behavior. And once I get more than 24 zeros, it'll actually, am I saying that right? Yes. Then it'll start becoming false. Because at 10 to the 40 times 10 to the negative 16, the gap is around 10 to the negative 24. So I can really go all out with this. Very weird stuff. Okay, yeah, you could do it with small numbers. And again, 10 to the 10 is going to be false. But I know there's this magical 10 to the 16 thing that we want to keep in mind. Okay, yeah, very abbreviated version of this lecture. You have 16 digits of precision to work with, which is kind of the same thing I was saying before. You can trust your numbers in base 10 up to about 16 digits of precision. Okay, let's skip over this thing marked as optional for now, and you can read over it later if you want. And now let's get to Ryan's question, which is, well, now you've told me how bad things are, what can I do about it? And it turns out, well, first of all, does this ever matter? And the answer is rarely, but yes. And then the second thing is, when it matters, what can I do about it? And amazingly, you can do stuff. So I've showed you this logistic regression loss in your lab, and I've just made a version of it with 1D. So W is just a single number, and then I don't need matrix multiplication. I just have regular multiplication, so everything's a bit simpler. So here's that same thing, sum log 1 plus x, and then I have just regular multiplication here because I'm assuming there's only one feature. And here's what I'm going to do. Comment this out for a second. I'm going to generate 100 random training examples, or I'm just picking random numbers. I'm going to generate a random weight vector. I'm going to generate random target labels. I'm just going to call my function and whatever some number. Okay, but hey, what if my training examples were big? Okay, I guess that could happen. I could have big numbers in my data set, even maybe after scaling, who knows? This happens. So it is going to be a problem if this happens while you're trying to do your training. So if your gradient descent or whatever thing is going to blow up in the middle, then it's going to ruin your computations. And so this is one case where these errors actually do come up and you actually do need to know about them. The other case where it comes up a lot is in that, another case where it comes up is in that lecture that I cut, which you can go look at if you want, which is about how to approximate gradients if you're not going to do the math by hand. Okay, so this is the function up there, sum of log of 1 plus e to the some stuff. And let's forget about the negative y wx for now and just call it z. Z means some stuff. At the end of the day, fundamentally, the computation we're doing is log of 1 plus x of some stuff. And we're getting the overflow when that stuff is large. Why is that? Well, because exp is, you're making a pretty strong statement when you exp something. You can just get overflows pretty quickly because it's, e to the power of something. It's a big deal. Oh no, entry. Okay, anyway. So, fine. Here's what you can do about this. So log 1 plus e to the z is only a problem when z is really big. Like, let's say z is 1,000, right? E to the 1,000 is some ridiculous number. Here's the beauty of it. E to the 1,000 is a ridiculous number. So ridiculously big that adding 1 to it is kind of a joke. I mean, adding 1 to 10 to the 100, like, it's completely and utterly negligible to add 1 to such a big number. And furthermore, you can't add 1 to such a number in floating point anyways because of this whole gap rounding thing. Even if you wouldn't overflow there, it would just round back down to that original number when you tried to add 1 to it. As soon as that number is bigger than 10 to the 16, you can't add 1 to it. That's like not an operation you can do anymore. So the adding 1 is not important. It's in the math because we derive something, statistics, etc. But computationally, we don't care about the 1. We care about the 1 sometimes when z is small, like if z is negative, the 1 is actually dominating over x to the negative z. But in the case we're having the problem, the overflow problem, when z is large, in that case, the 1 doesn't matter. So let's just throw away the 1. Goodbye 1. Now we can say 1 plus e to the z is roughly e to the z. And then log of 1 plus e to the z is roughly log x z. But log and x are inverse operations of each other, and we could just cancel them out. And so this allows us, so here's the original thing. That's just log 1 plus e to the z. Here's my function. Log 1 plus x safe. And it's going to check if z is big. And if z is big, it's going to say, well, that plus 1 wasn't going to do anything anyways. I'll just do that approximation we talked about above, namely log 1 plus x z approximately equal to z itself. So this code here returns z is this math up here. Else, if I wasn't about to blow up, then I'll just do the normal thing. Or you could even call the original function if you want to be modular and all those great things. Okay, so look, when my z is a regular innocuous number like 0, they produce the same answer. They produce the same answer because my safe function is literally calling the original function, because z is not greater than 100. But in scary cases where it was going to blow up, then my function is way better, because it returns an extremely close approximation to the right answer. The fact that we didn't add 1 to e to the 1000 is incredibly unimportant. And hey, we anticipated this, we dealt with it, and we have code that gets around it. Now, this is particularly a matter of overflow. Overflow means your number that you want is bigger than the biggest number. That's called overflow. And then it gives you that inf in NumPy, or it just throws a regular Python error if you're not using Python. So there's many types of errors we can talk about. There's the rounding error, which is what we talked about mostly, like with the gap and all that. That's the rounding error. But this is a simpler case. It's just overflow error that says the number we want is bigger than the biggest number. There's also underflow, where the number you want is smaller than the smallest number. So here's the greatest part. You might say, okay, well, I get it. If it was going to blow up, then anything is better than it blowing up. So sure, I'll take your 1000 over inf. But what about if I call it at 110? If I call it at 110, it is executing my if statement. It's not calling the original function. So now I'm going to get the wrong answer, because I've made an approximation when there was no need to make an approximation, because it wasn't going to blow up. But here's the thing. The thing is, they're indistinguishable. And they're indistinguishable because of this floating point stuff that we've already been talking about. That even though it was unnecessary to make the approximation, e to the 110, when you add 1 to it, numerically, because of the rounding errors we were talking about before, is still e to the 110. So it's fine. Like, there's basically no situation where our function is worse than the original function. It's either the same or better. And so, yeah, there is stuff like this literally inside the code of scikit-learn and SciPy and all these kinds of things when they make logistic regression and when they make, TensorFlow and stuff that we'll talk about later. Someone had to deal with all these things for the common loss functions and their gradients, because there's going to be problems if you didn't, and there's just like strictly better ways of coding it up that avoid these issues. Yeah, so it's very satisfying. I mean, we took the math side of things and the floating point side of things, and we wrote better code. I don't know, I think it's fun. Any questions? Yes, Tom?
I was just curious on why you picked the Z is greater than 100. I was just wondering why you picked 100.
Why did I pick 100? Well, if I pick it at 1,000, that's not good because it's going to overflow before 1,000. So if I pick 1,000, it's not really safe because it's just not calling the function early enough. If I pick 1, that's too conservative. And then when I call it on 2, I'm going to have induced an approximation for no reason. And so I want to pick something in between that was big enough that I didn't approximate numbers for no reason and get errors for no reason, but was small enough that it catches all the overflows. And so there's a range of acceptable numbers in there, and 100 is fine. Good question. Yeah.
Thank you.
Any other questions? So there's going to be some stuff in lab this week. You'll see at least one other case where thinking about this is actually useful and relevant, and that you yourself may have used functions that did this kind of thing before. Okay, more take-home messages. Yeah, right. Okay, we talked about all that. So, right. I mean, there's many reasons why we recommend not reinventing the wheel as like a general approach. Like, if scikit-learn has logistic regression, then use it and don't write your own logistic regression from scratch in case you need to. And if you had enumerated reasons why you didn't want to do that, well, you could have thought of a bunch of reasons like it's a waste of my time to write that code if someone else wrote the code. It has an open source community around it and people will update it, and mine won't get updated by random people, and their code is probably runs faster than my code because they optimize it. But now you have a fourth reason of why you might want to use existing code bases, is that they have thought through these sometimes hard to notice issues and dealt with all of them. And if you're going off and doing your own thing, you'll need to be careful about this.
This might be what we're doing later, but for neural networks, are we actually coding our own neural networks, or are we using like a...
No, for neural networks, we're going to use TensorFlow, which will function similarly to scikit-learn and do this stuff for us.
Okay.
Okay. Yeah, so this, we don't have to go through this in detail, but all I really want to say here is this is really not a contrived example, and like if you have, my demo was with one feature, but if you have more features and more classes and like the more stuff is getting added together, the more likely things are to overflow. So it's not at all far-fetched that this overflow would happen in a real scenario. That's all I really want to say. You can ignore the rest. There's an optional, a required lab question dealing with this as well. Okay, the last thing I want to say is very tangential, but I just wanted it to be said somewhere in the program, which is about taking the inverse of a matrix. So for example, in the regression course, did you see the normal equations? Yeah, so in the regression course you saw the normal equations, which says, whatever, W equals some X transpose X inverse something or other, times X transpose Y. So again, it might not be super likely that you end up doing this yourself, but if you do, it's good for someone to tell you that it is almost always a bad idea to take the inverse of a matrix. So NumPy has a thing, numpy.linearalgebra.inverse, take the inverse of a matrix. R has whatever it has, solve or something like that. But when you see that kind of thing, people tend to write it on like PowerPoint slides or on a blog, like the normal equations, and they'll put the little inverse sign, to the power of -1. But don't just go and code up what you're seeing on the page, because you'll run into disastrous things related to what we were just talking about. So almost always, what you have is some sort of AX equals B situation where A is a matrix. In the linear regression case, that's definitely the situation. And someone may write x equals A inverse B, which is fine mathematically as long as A is invertible, blah, blah, blah. It's not wrong to write that, but computationally you don't want to do it that way. So here's a demo. I have made a random 3 by 3 matrix, and I have made a random vector of 3 things in it, and then I have solved, so numpy dot inverse of A, matrix multiply B. That's exactly this thing up here. And I get, oh, well, I could print out the answer. I get something, and then I can use the numpy linear algebra solve function, which takes in A and B and does the same thing. And when I do that, I will get the same answer. And I can call this all close thing. If you haven't used it before, it's pretty useful. Because of these floating point errors and stuff, sometimes things are the same, but not quite the same. And you can just check if they're all close instead of all equal. It can be useful. So, okay, this is all fine. But now I'm going to pick a more horrible matrix that I happen to know is problematic, but not impossible to encounter in real life. And I'm going to do the 2 things, the inverse A times B, the solve. I'll check if they're all close. They're not. And so I'll say, okay, well, what's the difference between them? You know, is the number off by 0.001? Is it off by 2? It's off by 10 to the power of 117. So that's not good at all. And I can tell you it's y1 that's wrong and not y2. And so, again, this is just kind of, I marked this as optional, but since we had time, I'm talking about it. I'm not really going into the details. You can read more about it if you're interested. But just for your information, if you see yourself inverting a matrix in your code, ask yourself, do I really need the inverse of the matrix, or am I actually trying to do an AX equals B situation? If so, just use the solve functionality and it will avoid a bunch of numerical issues. So that's all for this class. Just a little roadmap for what's coming. So on Wednesday, we're going to talk about stochastic gradient descent, which is a variant of gradient descent. There was some talk in the Slack. People were like, gradient descent's so bad, why are we learning it? Yeah, it's pretty bad in a lot of cases. It's pretty slow in a lot of cases. But stochastic gradient descent, on the other hand, is super useful and popular. And we kind of need gradient descent conceptually to understand that before moving on to stochastic gradient. So we'll do that on Wednesday, and then we will do neural networks and deep learning for the rest of the course for the next 2 weeks. So that is it. I'll see you all in lab.